Artificial intelligence, AI, is the field of computer science focused on creating machines capable of performing tasks that typically require human intelligence, such as learning, reasoning, and problem solving. Driven by advances in algorithms, data, and computing power, modern AI now powers everything from voice assistants and recommendation systems to self-driving cars and advanced language models. Evolution of AI is contributed by many factors. Following are the key factors that contributed to the evolution of AI, each summarized in one sentence. 1. Hardware. The development of powerful parallel processing units like GPUs and specialized AI chips, TPUs, provided the massive computational power required for training complex models. 2. Algorithms. Breakthroughs in machine learning models, especially the transformer architecture, provided the core mathematical frameworks for modern AI. 3. Data. The availability of internet-scale big data served as the essential fuel for training and refining AI algorithms. 4. Infrastructure. The rise of cloud computing democratized access to the vast computing resources needed for AI development and deployment. 5. Open source. The proliferation of open-source frameworks, like TensorFlow and PyTorch, and models accelerated innovation and collaboration across the global research community. 6. Investment. Massive corporate and government funding created a financial runway for expensive long-term research and development. Please take into note that the development of this kind of video takes hours to days, so please support us with likes, comments and by subscribing to channel. The evolution of electronics, from vacuum tubes to transistors to integrated circuits and specialized AI chips, provided the fundamental physical components that made powerful and scalable computing infrastructure possible. So in this video we will be inspecting the evolution of electronics technology. We won't be focusing on electronics basics, individual concepts or components, however focus on the tech evolution of electronics. Here is the detailed evolution of electronics, with a focus on recent developments. 1. The vacuum tube era, early 1900s to 1950s. This era was defined by the manipulation of electron flow in a vacuum, enabling the first electronic systems. Tubes could amplify signals, rectify current, convert AC to DC, and act as switches. They made possible radio broadcasting, the first mass communication medium. Long-distance telephony, amplifying signals for cross-country calls. First computers, example ASIC, 1945, these were enormous, power-hungry, and unreliable due to tube burnout. 2. The semiconductor revolution and the transistor, 1947-1960s. The invention of the transistor was the pivotal moment, replacing bulky, fragile tubes with small, solid-state devices. The transistor, 1947, Bell Labs, Bardeen, Bratton, and Shockley, a semiconductor device that could amplify and switch electronic signals. Its advantages were profound: smaller size, lower power consumption, no warm-up time, and much greater reliability. Silicon and planar process, 1950s, Gene Horney. The development of the planar process for silicon transistors allowed for mass production. Silicon's properties made it superior to germanium, establishing Silicon Valley as the industry hub. 3. The integrated circuit, IC, and microprocessor, 1960s to 1980s. This was the era of integration, putting multiple components onto a single chip. The integrated circuit, IC, 1958, Jack Kilby, 1959, Robert Noyce. The concept of fabricating multiple transistors, resistors, and capacitors on a single piece of semiconductor material, a chip. This eliminated the need to wire discrete components together, enabling greater complexity and reliability. Moore's Law, 1965, Gordon Moore. The observation that the number of transistors on a chip would double roughly every 2 years. This became a self-fulfilling prophecy and a driving goal for the industry. The microprocessor, 1971, Intel 4004, the computer on a chip. It integrated the entire central processing unit, CPU, onto a single IC, sparking the personal computer revolution and embedding intelligence into countless devices. SMD, surface mount device/technology, is a crucial enabling technology that fits squarely into the transition between the age of specialization and scaling, 1980s to 2000s, and the modern era. It was not a new component like a transistor, but a revolutionary new method of assembly that allowed the theoretical advances of the IC and microprocessor eras to become practical consumer products. Without SMD, a modern smartphone's motherboard would be the size of a dinner plate. The miniaturization demanded by Moore's Law would have hit a physical assembly bottleneck. With SMD, it became possible to densely pack the ever-increasing number of components, ICs, resistors, capacitors, around a microprocessor, leading directly to the development of complex system-on-a-chip, SoC, designs and the devices they enabled. 4. The Age of Specialization and Scaling, 1980s to 2000s. As scaling continued, the focus shifted from general-purpose chips to specialized, high-performance designs. Application-specific ICs, ASIC chips designed for a particular application, example, for a specific modem or video game console, offering optimized performance and cost. System-on-a-chip, SoC took integration further by putting an entire system, CPU, GPU, memory, modems, etc., onto a single chip. This was crucial for the mobile revolution. digital signal processors, DSPs, and microcontrollers, specialized processors for real-time data processing, audio, video, and for embedded control in everything from cars to toys. The cutting edge, the Heterogeneous and Intelligent Era, 2010s, present. Recent developments are defined by the end of easy Moore's law scaling and a new focus on specialized architectures, new materials, and integrating intelligence directly into hardware. 1. Advanced semiconductor architectures. Beyond single-core scaling, instead of making one CPU core faster, the industry now uses multi-core processors, multiple CPU cores on a single chip for parallel processing. Heterogeneous computing, integrating different types of cores optimized for specific tasks on a single SoC, example, ARM's Bigdata, Apple's M-series chips mixing performance and efficiency cores. Chiplets and advanced packaging, instead of building one giant, monolithic chip, designs are broken into smaller chiplets, example, I/O, CPU, GPU, that are fabricated separately and integrated into a single package using advanced techniques like 2.5D/3D packaging. This improves yield, reduces cost, and allows for mix and match components. Example, AMD's Ryzen and EPYC processors. 3D stacked transistors, example, Intel's Ribbon FET, Samsung's MFET, the next step after FinFETs. Transistors are stacked vertically like ribbons, allowing for a dramatic increase in transistor density without needing to shrink them further horizontally. 2. The rise of domain-specific architectures. With the slowing of general-purpose CPU gains, performance leaps are coming from hardware designed for specific workloads. AI accelerators, the most significant trend. These are chips specifically designed for the massive parallel computations required for AI. GPUs, graphics processing units originally for graphics, their parallel architecture made them the default for AI training. NVIDIA dominates this market. TPUs, Tensor Processing Units, Google, custom ASICs built from the ground up for TensorFlow AI operations. NPUs, Neural Processing Units now a standard part of modern smartphone and PC SoCs, example, in Apple Silicon, Qualcomm Snapdragon, AMD Ryzen AI, to run AI tasks efficiently on-device. Quantum computing chips, while still embryonic, companies like Google, IBM, and Rigetti are building specialized superconducting chips that manipulate qubits to solve problems intractable for classical computers. 3. Novel materials and post-silicon explorations. The industry is researching successors to silicon to overcome its physical limits. Wide bandgap semiconductors, gallium nitride, GaN, and silicon carbide, SiC. They operate at higher frequencies, temperatures, and voltages with greater efficiency than silicon. They are revolutionizing power electronics, fast chargers, EV powertrains, renewable energy inverters. 2D materials, materials like graphene and molybdenum disulfide, MOS2, are just one atom thick, offering potential for ultra-low power and flexible electronics. Neuromorphic computing, chips that mimic the architecture of the human brain, using spiking neurons instead of traditional binary logic. They promise extreme energy efficiency for specific AI tasks. Example, Intel's Loihi chip. 4. Pervasive connectivity and sensing. 5G per 6G RF chips, advanced radio frequency chips and mmWave antennas that enable high-speed, low-latency wireless communication, forming the backbone for IoT and connected everything. Advanced sensors, the proliferation of sophisticated MEMS, micro-electromechanical systems, sensors, Lidar for 3D mapping, high-resolution image sensors with computational photography, and environmental sensors in every smartphone and vehicle. Thanks for watching the video. In future videos we will be deep diving to the other factors contributed to AI's evolution such as hardware, algorithms, data, infrastructure, open source tech, and investment and policy evolution.